In the present times with ever-growing bandwidth demands, where gigabits are not enough, and the 2021 world record was set for transmitting 300 terabits over a 3000 kilometers long-haul distance cable.
Exactly. Why would anyone care about historic 10BASE2 networks which carried only a meager 10 megabits anyway?
Let's talk about legacy network technology. I'm the Vintage Collector and these are my stories.
So before diving into all that neat gear, I think I must first establish a bit of network terminology.
Oh no, not those boring OSI layers.
Actually, it's not boring, but rather a very useful thing, helping to understand how things work. And in very simplified terms, it all stacks up bottom up, right away from the physical layer all the way up to the application layer. Now the physical layer, also known as layer 1, in traditional understanding includes the physical structure. So basically the cables, whether that be copper cables transporting electrical signals or fiber optic cables transporting optical signals, in other words, light. In a very abstract way of thinking, for wireless networks, layer 1 also includes the air as it's the transport medium for the radio signals. In context of 10BASE2 networks, we don't use twisted pair cables, but a coaxial wire, which bears the boring name of RJ58. There's a similar cable going by the RJ59 designation, and the main difference between the two is the impedance, which is 50 ohms for the RJ58 and 75 ohms for the RJ59, both of which can be used. While this cable is still used for radio communication systems today, its days for Ethernet networks are long gone. 10BASE2 had some nicknames, like Thin Ethernet, which was coming from the direct comparison against the bulkier 10BASE5 Ethernet. I'll come back to that one again in a moment. Let's look first into why 10BASE2 was also called CheaperNet. Simply put, because the thinner cable was actually less expensive than the 10BASE5 thick Ethernet cable, and it used a lot less of equipment required to hook up a machine to the network. In its most simplistic form, all you needed is an RJ58 cable, 2 T-pieces and 2 terminators. So much so for the layer 1 components. Then you also needed some network cards. Although these are physical devices that plug into some machine, a network card is considered an active component and belongs to layer 2. We'll learn later on why that is. For the initial setup, let's connect those T-pieces onto the BNC connector of the network card. The terminators go to one end of each of the T-pieces, while the network cable plugs into the other end of the T-pieces. Voila! This is a 10BASE2 network in its most simplistic form.
And simplicity is key, especially when you're consuming services like the ones provided by today's episode sponsor, PCBWay. I had worked with PCBWay on various 3D printing projects previously featured on this channel, like this beautiful reproduction of a power supply cover and the drive sled for my SGI O2 workstation. Right now, I'm looking forward to the results of our current collaboration around turnkey PCB production and assembly services. And that was just about in time, as PCBWay cut their fees for PCB assembly down to $29 per 20 pieces, as I need just that electronic spare part to bring this IBM P70 back to life. So if you need services, PCBWay is here to make it happen.
If I plug those network cards now into some computers, it would be enough to install some network software like Lantastic or Windows for Workgroups to make the computers communicate to each other. And to extend this network, I can simply remove one terminator, plug in the next RJ58 cable and feed it to the next network card. It's as important to not connect the cable in a loop. The 10BASE2 backbone is indeed a two-ended network, which needs to have those resistors at the terminating end. Also, you can't create a bus with the T-pieces in between and then simply extend the wire out the T-piece into the NIC. That would make sense, of course, from an in-house cabling perspective, but that doesn't work with the equipment I've shown you. There was, however, a means to accomplish this, for example by these EAD wall plugs and those special cables which, if you watch closely, consist of two actual wires leading out towards the BNC connector. This particular wiring setup is defined as a bus topology. On the present day, with fiber optic and twisted pair Ethernet cabling, we use a combination of star, tree and sometimes even meshed topologies. For 10BASE2 it's straight and simple, one single wire which also points at one of its deficiencies. Is the wire disconnected or cut, or a terminator is missing, the communication breaks until the issue is fixed. That's because the electrical signal is being reflected through the wire, which will disrupt the entire network segment. Now imagine trying to find the cable breakage given the maximum length of a 10BASE2 segment of up to 185 meters. In practice, 10BASE2 limits you to 30 nodes per such segment and a minimum distance between nodes of 50 centimeters. So despite the hypothetical limit of 185 meters, what if you wanted to connect more than 30 machines? This is where the 543 rule comes in. You can connect up to 5 segments of 185 meters. Let's look at this device here, which is actually a combo device being both a 10BASE-T hub and a repeater for 10BASE5 and 10BASE2. So this lets me interconnect at most 2 different segment technologies, increasing my reach and the number of nodes connectable to the network. This one is certainly interesting, as for one you could run it just as a 10BASE-T hub when disabling the backbone function. With the latter being enabled, you could choose between connecting to a 10BASE2 or a 10BASE5 network. And if you so chose to, you could spare the T-piece and the resistor if you enabled the internal resistor for the 10BASE2 segment. And here's a smaller repeater device that can just extend between 10BASE-T and 10BASE2 to compare. And in case you're wondering what's this little switch for MDI and MDI-X. Back in the day, you used straight cables between the hubs and workstations, and crossover cables between hubs and hubs. If you didn't have a crossover cable, you could tell the hub to perform an internal crossover when setting to MDI-X. This is also where the term of so-called uplink ports come from, as if at all, this function was only present on designated uplink ports. This has largely disappeared ever since, as on the present day, switches have auto-sensing and perform an internal crossover automatically, so you don't really need to worry about a straight or a crossover cable anymore. So if I were to extend my network segments now using those 2 repeaters I have, I'm totally fine, as I can mix up to 3 segment types, 10BASE5, 10BASE2 and 10BASE-T. Also, for me that means I have no more than 3 segments in total. So the 543 rule is not violated. As far as repeaters and hubs are concerned, these belong to layer 1, so the physical layer. All they do is transmitting electrical signals or even amplify them at the example of a repeater. But what they don't do, what makes the big difference to a switch or a bridge, they don't look at layer 2 frames at all. Now, I don't have a bridge to show, and as far as 10BASE2 is concerned, there was no switches. But as noted earlier on, the network cards are considered layer 2 devices. Layer 2 is the data link layer where the physical addressing is applied. Maybe you heard about MAC. No, not the Macintosh, but Media Access Control. Every network device has a so-called MAC address, which is a physical device address. And this address is used by data link layer protocols like Ethernet and Token Ring for addressing the frames.
Wait a second, serial interfaces don't have MAC addresses.
Yeah, that's true. There's many different protocols that go along with many different interface types. Let's take frame relay as an example, which uses so-called data link connection identifiers, DLCI for short, which serve the same purpose. And that's also the reason why, for example, Ethernet switches belong to layer 2, as these are keeping track of the MAC addresses in an internal table, the MAC address table. In other words, a switch notes the port it learned a particular MAC address from and will forward the frames targeted for any given destination MAC address only through that port it was learned from. A hub or a repeater simply won't do that, as it will just take any electrical signal it gets and passes it all along as it comes. That's also one of the drawbacks of 10BASE2, as with its single wire bus design, all connected stations are technically in one huge so-called collision domain. And the more stations are connected, the higher the probability of a data collision on transmission is. For Ethernet, CSMA CD, carrier sends multiple access collision detect was invented. Any connected device is listening on the wire if there was a pending transmission and starts sending only if the medium is free. Of course, it could happen that two stations simultaneously came to the same conclusion that the wire is free and started transmitting, which would lead to a packet collision. In this case, a jamming signal would be sent, causing these stations to back off and retry later on again. Needless to say, this quickly became a problem with many stations in the same segment and thus collision domain, and increased in probability the chattier the network was. This was essentially solved by introducing switched networks, where the typical star topology introduced point-to-point links between the station and the switch, reducing the collision domain just between the two. Lucky you if you had already network cards supporting multiple wiring standards. Like these ISA-based network cards, of which this one by 3Com offers both the BNC and the RJ45 connector for 10BASE2 and 10BASE-T respectively. I also managed to obtain an 8-bit ISA network card, which I do hope to get to run in an old-fashioned IBM PC or PCXT. If you watch closely, you'll see these jumpers down here, essential for configuring the hardware I/O address. The previous card I've shown doesn't have it, which means it's software configurable, but this one needs physical configuration. For certain, this is an earlier generation network card as it supports both the BNC connector but also the AUI, the attachment unit interface. Using the latter, this card could also connect to a 10BASE2 network. Last but not least, this network card by Acton even has all three connector types. Besides that, I also have these network cards. The connector looks a bit like PCI at first, but these in fact are for the microchannel architecture, MCA for short. I have this IBM P70 which still needs a repair, but I do have to get it up and running to make use of one of these network cards. And here's a PCMCIA adapter card intended for a 90s era laptop, providing the attachment unit again suiting for both 10BASE2 and 10BASE-T. Now, 10BASE2 was introduced in 1985, offering a throughput of 10 megabits per second. 10BASE-T with the twisted pair cabling standard appeared in 1988. As noted in my earlier episode on Windows for Workgroups, the initial release of Windows for Workgroups 3.1 had failed miserably when it came out in 1992. According to Raymond Chen, this was also because it originally came bundled with a network card, but not one for the increasingly becoming popular 10BASE-T standard, but the one that just had the BNC connector for the 10BASE-2 networks. Having said that, maybe things would have played out better if they used at least a combo card like this one. But as we have seen, there were even those cards which have all three connector types. The attachment unit interface was as mentioned needed for 10BASE-5 networks, and while transitioning from one standard to another, it would have been certainly a nice thing to keep the old network cards. This is where these adapters come into play. And although they stick into the AUI connector, these are electrical converters and thus considered layer 1 devices. The AUI connector has this slider which locks the AUI plug into position so it can't fall off. And of course, for this particular network card, which has already a BNC connector, using the AUI to BNC converter really doesn't make much sense. And this one here also doesn't make much sense, as even for a NIC with multiple connectors, only one could be active at a time. Still, if you never have seen it, for 10BASE-5 you'd have a cable using a DB15 connector running from your station all the way into this AUI. The AUI, which came with a piercing tap, also known as vampire tap, would be hooked up to the main coaxial cable and literally pinch it to make a physical connection to it. Yuck. So apparently 10BASE2 had its advantages over 10BASE-5 for simplified and less costly cabling and easier expandability. Now, as the last devices to show, here's some more media converters. These plug basically into an existing 10BASE-2 segment on one end and a 10BASE-T segment on the other. In a way that's similar to the repeater I've shown you before, just with the notion that these media converters don't do any signal amplification. They're more comparable in function to the AUI converter we just saw before. So that was now a lot of fundamentals on 10BASE2 and a tiny bit on the OSI reference model.
Yeah, I was missing the practical hands-on.
Don't worry, this will come in my next episode when I'll put all that gear to use. And if I was too talkative today, then I'm sorry, but as a network engineer, I could talk about this topic for hours. What was your experience, the good and the bad, with 10BASE2 networks? Let me know in the comments below. I'm the Vintage Collector, and this was my story for today. Thanks for watching, and see you again next Sunday. Next on the Vintage Collector. So let's put that network gear to some use and see if I can bring one of these IBM PCs onto the network. And I'll be trying to get PCMCIA to work on one of these 90s laptops, and I will definitely be expanding this old portable machine with a network card as well. But then I wondered if I could get good old Doom to work over an IPX network.